this is where we ended off last time, and today I want to do some refactoring, hopefully quickly, to prepare for some of the math that we're going to need for particle collision. First of all, I think I want to let's try and make the parameters good for testing collisions. So I'll just reduce gravity to 0 and then reduce the number of particles that we're spawning to, let's just do 2 particles and we'll make them pretty big. Let's make them like 50. So now we should be able to see if they run into each other, and after we implement the collision, we should be able to see that they will bounce off each other if we get lucky, I guess. So right there, we should have seen a collision. And particularly today, what I want to change is I want to do some refactoring of our struct and change to using the vectors that Verlet provides. So for most of these parameters that we have like an X and Y component. So vector 2 should be good for us to switch over to. I think for X and Y, we can define a new vector 2 and call it pause. And same thing for velocity and acceleration. And in our, let's see, I guess we'll just go through one by one and update these to use the vector math. So for things like just doing addition, there should be a vector function called vector2 add, where you put in vector 1 and vector 2, and it should do a vector addition. Let's do the same thing for position and velocity. And for our wall collision, we are going to need to change this to be pause.x. I think this is how you access the first component of the vector, unless I'm wrong, but I guess we'll see. Okay, I think that looks good. And let's check what else we need to change. I guess here we need to change this to also grab the position, X and Y. And let's see, instead of passing in these arguments, we can define some defaults in our struct. So we can, by default, make this, for position, we want to get a random value. So let's just grab this from here. And same thing for velocity. But we can set this to be something like -10 to 10 for both X and Y velocity. And acceleration, we can set the X acceleration to 0, and let's leave Y as gravity since we can control that up here with our global variable. And then radius, we can set to be, let's just say 50 for now. And now I think we should be able to remove all of this and then just call the default constructor. And let's see if this still works. I'm not sure if there's something I missed. Okay, so we're not seeing the function vector to add. So maybe I need to include ray math. So that fixed it, but now we are not seeing any motion. So let's see if I have something that I missed here. Oh, actually, I think I need to just update the value of velocity to be the result of this. Same thing here. Wonder if that fixes that. Okay, perfect. So it looks like everything is working fine. So I believe we have successfully refactored to be using vectors now. One other thing is we can, I guess this is a big design choice, whether we want to use like object-oriented programming or stick with like kind of this more functional design. I'm not really sure what you would call this design right now. I'm thinking whether we want to add like an update method to the ball objects themselves so that we can just call ball.update. Or I think at the very least for now, I will just separate these, what we're doing inside of this update function to be their own functions so that it's a little bit more readable. And hopefully that doesn't affect performance. But for right now, I think it should be okay. And we can think about optimization later. Let's just create functions like update velocity, update position, and then update wall collision or something like that. We'll call this handle wall collision. Take in a reference to a ball and just copy and paste this in here. And then we can call handle wall collision for this ball. Hopefully that still works. Let's see. Okay, it does not work. Was not declared in this scope. Why is that? Oh yeah, I need to give a type here. All right, so that looks like it still works. And it looks like we're in a better spot now to, we have some better organization in our program. For now, we can, let's do some of the optimizations that we were talking about in the last video. So let's just make this a configurable constant, call it num particles. And we can, when we create our vector, we can reserve that number of particles because we don't expect to be changing that throughout the length of this particular simulation. And instead of doing pushback, let's do mplaceback. And I don't think we need to pass, how do you do mplaceback without passing in any constructor arguments? I think if this is empty, the compiler should know that since this is, it knows the type of the object inside the vector. So I'm hoping that this still works. Okay, and then now we can just create our constant num particles and just put it up here. See if this still compiles. Sweet. All right, so that looks good to me. All right, so now to talk about adding a collision between our particles. This is actually my second time recording this portion of the video because the first attempt didn't go so well. So I have more of a game plan now. And these are the three things that I think we need to implement to have a stable collision detection algorithm. So the first thing I will talk about is substepping, and then something called Verlet Integration. And then finally, we can implement our elastic collision between particles. So substepping is a little bit difficult to explain, but it's essentially allowing the CPU to calculate the position, like update the position, acceleration, and velocity of the particles multiple times in between when a frame is drawn to the screen. And what that allows us to do is just have a little bit more accurate calculations for those three values. And without the substepping, sometimes we'll get with like a high number of particles, we can see that they'll sort of like phase in and out of each other or kind of jiggle or wiggle, and they kind of never stop because of the way that we're calculating these changes in velocity and position. So the way that we want to do this is basically we will have a substep, like a number of substeps, which is again the number of calculations we want to perform before actually rendering the final position to a frame. So what we can do is we can use this RayLoop function called getFrameTime, and we will call getFrameTime in our main loop. We will call FrameTime will be getFrameTime. And then we can say dt will equal FrameTime divided by our number of substeps. And let's define our number of substeps up here as a constant again. And we'll just set it to 8 is what I've heard is a stable value for now. And now that we've defined our number of substeps, we need to go back to main and tell the update loop to calculate, we want it to update every, like basically number of substeps every frame. So we can do that with a for loop, and we'll say from I up till the number of substeps, we will call our update function. And then we also need to pass in our delta t like this, and then update all of the functions within our update function. So update will now take in a float called dt, and then velocity will also take in dt, and update position will take in dt. And then up here we will say float dt, And the new method for updating velocity will be essentially this: velocity plus acceleration scaled by delta time. So this will look like this. We'll calculate the acceleration per this frame. We're multiplying the acceleration by a scalar called dt. And then we will add this to our current velocity. And for our position function, we will update this as well, like so. And now, let me see if I missed anything. I think this should properly implement our substepping. So let's see if this compiles. All right, so we notice that these particles are moving very slowly now, and that is expected. But we basically want to, I think now we can just scale our initial random velocities by some number like maybe times 10. And hopefully this still works. So it seems like they still bounce off the walls properly, and we still haven't implemented the collision between particles, but let's make this even faster. Let's make this like 1,000. Okay, so this is working fine now. So it looks like we should have properly implemented our substepping. And the next thing I want to talk about is Verlet integration. So I don't think I can talk in depth about Verlet integration because I don't really understand it completely because I haven't just taken the time to look into it. But basically, it's a different way of updating our position variable. And instead of explicitly keeping track of velocity, there's basically a different equation that we can follow. And the benefit of this is that it is more stable in these sorts of particle simulations. In the first attempt, I tried to implement our collision detection. It resulted in basically a lot of jittering and the particles would never stop moving. And I suspect that it was due to our update function. So I'm hoping that when we implement Verlet integration, it will basically just have a much more stable simulation. So there's a couple things that we need to do to implement Verlet integration. And the first thing is we need to track, instead of tracking velocity explicitly, we will add a new member variable. So we will add a vector 2 called position old, and then we're able to get rid of our velocity because velocity is calculated implicitly through the change in position per delta time, essentially. And for the future, we'll just go ahead and add mass here. This is not related to Verlet, but for collision, we will add a mass and we'll just make it related to the radius for now. So now the way to implement Verlet integration is we can essentially write a new update position function, and we're not going to be using these anymore. So I'll just call it update position Verlet for now. And this will take in reference to a ball and also delta time. And I'm not going to explain this in detail, so if you're interested, just go look up Verlet integration on YouTube or Wikipedia and read about it yourself. But I'll copy in the code here for implementing the Verlet integration. Okay, so now that we have a new function here, we will, instead of calling update velocity and position in our update function, we can replace these calls with update position Verlet, pass in our ball object and our delta time. And now one other thing we need to do is update how we are handling wall collision to implement Verlet's integration. And what we can do here is do a couple of updates. And again, I'm not going to explain this in detail, so please look it up if you're interested in understanding it. But I think the more interesting part is just understanding how this works in the context of a C++ program. So I will just copy in some code here now. Okay, so hopefully I have typed this all correctly, and we have added a new bounce variable here, which we can configure to affect how bouncy the particle is against the wall. But let's try and see if we can run this and see if it still works as expected. Looks like I have an issue here on line 35. Okay, we need to just comment these out because we've changed the struct. Another issue on line 28. Oh, this was supposed to be uppercase. All right, something is wrong here. Let me take another look at this. Okay, I think the issue was that we were not setting our position old. We didn't give it a default value. The thing that we need to understand about Relay is that it calculates velocity based on the difference between its current position and its old position. So we can't actually just put a value like 0 in here. If we wanted to give it a velocity of like 1 and 1, we would need to basically subtract a 1 and 1 vector from our current position. So I think we can use something like vector to subtract from current position, and then we can give it a vector like -1 and -1. And let's see if this fixes our issue. Okay, so it looks like that works. Let's just see what happens when we spawn 10 particles, see how this holds up. All right, still looks good. So it seems like we were able to successfully implement our substepping and our relay integration. And the next thing we can do is work on our collision detection. So let me delete this old version and let me just change the name of this to be update position. And over here, we can remove that as well. For elastic collisions, detecting collisions should be pretty simple, at least between two circles or the particles that we are rendering to the screen. And then the actual math of the collisions is a little bit more complex. So we'll get to that when we get to that. But let me implement the collision detection right now. If we want to detect if two circle particles are colliding, what we can do is essentially calculate the distance between their center points and compare that to the sum of their two the radii, radius 1 and radius 2. So if two particles, the distance between their center point is less than or equal to the sum of their radius, then they are colliding. And obviously, if they are far apart, then they are not colliding. So this should be a pretty simple formula to implement in our program. So let's try and write a detect collision function. So this will be a Boolean function, and it will be is colliding. And we'll take two particles. And I think we can simply return, if their distance is less than or equal to the sum of the radii, then we can return true. And we can use a function from raylib that is vector to distance. And we can use that to calculate the distance between the center points. And let's just put these in parentheses here like this. And if we did this correctly, we should see that we can detect collisions. And I think just for fun, we can actually, let's try and see if we can change the color of the balls every time that they are colliding. So I think that we can, in our struct, we can add another member variable called color. And by default, we can give it the color green. Let me look up the raylib cheat sheet and see how we can change the color of them. I think we can use this function color from HSV, which is, it takes in a hue, saturation, and a value, and we can just increment hue by some number every time that we detect a collision and see what that ends up looking like. So we can give it a default color of green, and I think that we actually need to, what should we do here? In our update function, we need to call, let's do if is colliding, or actually, let's see. Maybe we need to do another separate for loop here, so that we can handle the objects by their index. So we have the constant number of particles, so we can use that as our bounds. And I'm going to be using a double for loop here. And we don't want to check if a particle is colliding with itself. So we will start the index for the inner loop we'll start it at I plus 1, and then we will go up to the number of particles and increment j. And basically inside of this loop, we will handle our collision between particles. So we can say if is colliding the object at index I and pass in the object at index j. If they are colliding, then we can just we can update the color of both of the balls, let's say. So we can say balls I dot color. We'll give it a color. Let me see what the function was called. Color from HSV. Well, I think actually, since it already has a color, we need to get color to HSV and then change that to an HSV. So we can say color A will be color to HSV. Color B will be the same thing. And we want to update it like this. Balls I dot color will be color from HSV. Okay, if I'm not wrong, this should basically change the color by a hue value of 10. And I think actually we can mod this by 255. I'm assuming this is a, what do you call it, 8-bit color or something like that. There's probably a better way to do this, but this is what is coming to me first. So, okay, if we implemented this correctly, I think that if the particles collide, they should change color. And let's see. All right, we have an issue here. I think we need to give this a type. Hue, saturation, and value. Oh, this should be a vector 3. Maybe they are just called X, Y, and Z. Let's just try it without the mod and see what happens. We got a seg fault. Oh, it looks like we have a typo here. So this should be J. Okay, so now we can't really tell if they're changing color. Doesn't look like it. All right, so I used Gemini to help me find this bug. I'm adding this fmod function here to make sure that we're not going past the maximum value of our hue. So every time it gets above, I think 360 is the maximum hue value, it'll basically do a mod. But that wasn't the issue. I think the issue is in our draw function. I forgot that we are explicitly drawing green particles every time. So we need to change this. And now that we've switched over to using vectors for our position and velocity, there's actually a draw circle vector function, and we can actually just pass in ball.position, ball.radius, and our color. So instead of always drawing it green, it should just grab the actual color from that object. Let's see if this still compiles. Okay, so now we have colors that are changing. And I think this is working as expected. The reason that these are flickering is because we're not actually handling the collision, so they're just moving together, and they're constantly updating their color. So this looks pretty cool. I think to make the movement more random, actually, we can also add a, let's see, maybe we can change this to be a random value between some numbers. So get random -3 and 3. Probably we'll still see the same flickering, but maybe it'll look more interesting. Okay. Yeah, cool. All right, so we've successfully implemented our collision detection. And the next thing is we need to actually handle the collisions and resolve basically the bouncing between each particle. To do that, again, I am going to probably not explain in detail what's going on here, but I'm essentially copying a solved equation and just implementing it in code. So let me add this function handle particle collision. And it will take in 2 of our ball objects. And essentially, we are just going to, when we see that particles are overlapping, we're going to move them apart from each other. And due to the way that the Verlet integration works, this is basically going to handle our bounce automatically for us. So if you're interested in that, I think you can look up a YouTube video about Verlet integration. And I'm just going to implement this code right now. Okay, so this is a pretty simple function here. Well, it looks simple, but I think the math is a little bit more complex, so I won't go over that. But essentially, this is going to handle our collision between particles in a theory. And finally, we need to add this function call into our loop. So let me figure out where we want to put that. I believe we want to put this in our, so this is where we're handling colliding. So we will want to handle collision for ball at I and ball at J, because this if statement already is screening out the particles that are not colliding. I think we can keep this color changing mechanism for now, just in case it makes it a little bit more interesting. And let's see if this runs. Oh, whoops, I need to, this is the vector that we are calling. Oh, it looks like I just forgot a couple lines of code here. Let me add these. All right, I just copied that equation incorrectly. Let's see if this runs now. And there we go. So it looks like the particles are colliding correctly, and they change colors every time they collide. Let's run this one more time. So it seems like they go super fast in the beginning, and then they lose a lot of energy. Let me see if I can tweak some of the parameters and see if we can make this look a little bit more natural. All right, so with a little bit of research and help from Gemini, I have added some modifications to our handle particle collision function. So previously we were just doing a static resolution, which is the not allowing the particles to overlap. We were pushing them away from each other if that happened in a certain frame. But we added some extra logic here to also account for some what's called dynamic resolution, which is to calculate the new velocity based on the distance that it was pushed apart. So again, not going to go too into detail on this because I honestly don't understand it 100%. But we added this new global constant called restitution, which is going to affect how bouncy the balls are. And now that we've made these changes, we can see that the simulation is now, I think it's running pretty much perfectly. So previously we were losing energy and the balls kind of slowed down very quickly. But since we are modeling elastic collision, I think this is probably more accurate to what we should be seeing, where the balls are not, doesn't appear to be like that they're losing energy every time that they bounce off the walls or each other. All right. I think one final thing for this video is I just want to check the performance of this, since I know that this is probably pretty inefficient since we have an n-squared algorithm where every ball has to check whether it's colliding with every other ball every frame, and every frame is doing that calculation 8 times. So I want to see how this scales when we up the number of particles to maybe 100. And let's also change the radius of them to something smaller. So this seems to actually be working pretty well. Still locked at 60 FPS. And I don't see any weird physics behavior, and seems like every ball is behaving correctly. Let's see if we can bump this up to 1,000. Reduce the radius to like 5. All right, so it's still running, and I don't see any weird behavior. But our FPS is now around 24, so we're definitely approaching the limit of performance for this sort of algorithm. But in any case, I think this looks pretty cool. I also want to see what happens when we enable gravity. Right now our gravity is set to 0. So let's reduce the number of particles to maybe like 300. And let's give this gravity some value. I'm not sure the scale we need, so we'll adjust. That seems like it's too low, so let's do like 100. Still seems very low. Let's try 500. Okay, I can't really tell, but it looks like they are moving down. Oh, I think one thing is we also need to decrease the restitution. So let's make this something like, I'm not sure, 99 for now. And we should start to see that they are losing energy eventually. Maybe we can make this much lower. Okay, now they're definitely starting to fall down towards the bottom. Pretty awesome. So seems to be very stable. So like I said, in the first time I tried recording this, without using Verlet integration and without using substepping, when the particles would settle at the bottom, they would kind of just jiggle around, and I could never really get them to stop, no matter what I was trying. But it seems like Verlet integration is a combined with substepping is a very stable way of calculating the particle motion. Right after this, I'll put in some footage of me playing around with some of these parameters and just trying to make cool patterns and see how the performance of this simulation pans out. Next time, we'll talk about optimizing this further, and thanks for watching.